Elon Musk's controversial Neuralink is ready to test its brain chip implant on humans.
Elon Musk's brain implant startup Neuralink is recruiting patients for a clinical trial.
In this video, I'm going to break down all the latest advancements in brain-computer interfaces and bionic vision, from the revolutionary technology to the complex surgery it requires, as well as its unfortunate complications. And I'm going to talk about why this technology will change life as we know it. Elon Musk has publicly announced that his startup Neuralink and its cutting-edge brain implant technology will aim to restore vision and cure blindness.
The first two applications we're going to aim for in humans are restoring vision.
And this is not some future projection. This is reality now. Neuralink recently received FDA approval to begin human clinical trials, and in 2024, Neuralink will be implanting their microcomputers into human brains on real, live people. And they'll be using automated surgical robots to perform the surgery. Neuralink's technology and brain-computer interfaces will change humanity forever. So let's get you up to speed with what's been going on behind the scenes. By the way, I'm Dr. Michael Chua. I'm a board-certified ophthalmologist with Puente Hills Eye Care, and I make videos to help you see better, look better, and feel better too. So let's take a step back. Implantable microchips, robotic surgery, brain-computer interfaces, what exactly are we talking about here? If you can see me talking to you right now, it's because there are light waves coming from your screen onto your retina, or the thin layer of tissue in the back of your eyes that detects light signals. Our retinas take these light signals, then convert them into electrical signals, which can get sent along the optic nerve to the visual cortex in the back part of our brains. So if any component along this pathway is malfunctioning, perhaps a cataract or clouding of the lens in your eyes is preventing light from hitting your retina, or maybe glaucoma is causing damage to the optic nerve. If any portion of the visual pathway isn't working, then we will have problems in our vision. And one of the fundamental concepts of how our visual system is designed is what's called the retinotopic map. What this means is that our brains organize information about where things are in the visual world around us. So each neuron in the visual cortex, or the part of the brain that's responsible for our sight, each neuron will fire based on a small part of the visual field, which is called its visual receptive field. And the way the map is set up, it's inverted. So, for example, if you see something here on the right side of your visual field, then a neuron will fire here on the left side of your brain. And then if you see something on the left side of your visual world, then a neuron here on the right side of your brain will fire. To really illustrate this point, look at this figure from a paper published in 2017. We're looking at the visual cortex of a mouse brain, and we're seeing the mouse's brain activity light up as the mouse watches a dot moving around. The way the mouse's brain set up is like our brains too. It's inverted, so when the dot moves up, the bottom part of the brain fires. And then when the dot moves down, the top part of the brain fires. With this information, scientists can basically map out each point in our visual world with a specific location in our brains. The reason why this knowledge is so powerful is because, in theory, if you can stimulate specific neurons in our visual cortex in just the right pattern, you can recreate the experience of seeing the world around us. For example, if you stimulate neurons in the brain in the pattern of a triangle in just the right location, you can have a patient see a triangle. Or maybe if you wanted them to see a smiley face, you can do that too. And that's basically the premise of these computer vision, computer brain interfaces. With our natural eye-brain interface, our retinas and our optic nerves send vision data from the world around us to our visual cortex for processing. But with Neuralink's technology, they're basically replacing the eye and the optic nerve component with a camera and a computer instead. This is, of course, a lot easier said than done. And in order for them to pull this off, it will require countless hours of research, hard work, and, well, money. As of late 2023, Neuralink has raised over $320 million to fund its research efforts, and the company has been valued at more than $5 billion just based on the potential of the technology it's developing. Now, the concept of brain-computer interfaces is not new. In fact, researchers have been working on this technology for decades. I can actually remember one of the most impactful lectures I listened to when I was a freshman in college. I was in an introductory neuroscience class, one of those big lecture halls, and there was a guest speaker talking to us that day. His name was John Donahue. I didn't know it at the time, but Dr. Donahue was actually one of the pioneers, one of the godfathers of computer-brain interfaces. During his talk, Dr. Donahue showed us videos of the technology he had been working on for years. He and his team were implanting electrodes or computer chips into people's brains and plugging them into computers. And I distinctly remember this grainy footage he showed us. He had patients who were paralyzed either from trauma or other spinal cord injuries, and with his technology, they were able to control computers, not with a mouse or a keyboard, but entirely with their minds. And they even had patients moving prosthetic limbs, all with their thoughts.
Now close it.
Now close. Nice. Open. Not bad at all.
This was in 2009 or 2010, and seeing this technology give people the power to physically control the world around them with just their thoughts, this expanded my reality of what was possible with science. This Neuroscience 101 course actually sparked an interest for me in neuroscience and neuroscience research. I ended up majoring in neuroscience during college and also joined a lab to do vision research for the next 3 years as an undergraduate. And coincidentally, our lab happened to be next door neighbors to Dr. Donahue's lab. I didn't realize it at the time, but during my time doing research in college, I enjoyed a front row seat to watch the development of brain-computer interface technology. I carried my interest for neuroscience and vision throughout medical school and ended up pursuing a residency in ophthalmology. And as I traveled to different vision and medical conferences to present whatever ophthalmology research I was doing at the time, there was always one team's work that piqued my interest at these meetings. That was the work of a company called Second Sight and their retinal implant called the Argus 2. The Argus 2 was the first ever retinal prosthesis that delivered bionic vision to patients, and it received FDA approval in 2013. How the Argus 2 worked was, first, patients would receive surgery. A small electrode, or basically a little chip that conducts electricity, would be implanted into the patient's retina. Here's a surgical video of a retina surgeon implanting an electrode into a patient's eye. So we're looking at the inside of someone's eyeball. This is their optic nerve here, which connects to the brain, and this electrode is being placed onto the macula, or the central part of the retina. Once that implant is set up, the patient is given a pair of sunglasses with a small video camera in the center to capture incoming images. That video data is then sent to an image analyzer, which processes the visual images. For example, the processing unit would run an edge detection algorithm, so it could create a mosaic of low-resolution pixels that resemble the object that you're looking at. So this image of a bike might be what the camera captures, but after it gets sent to the visual processor, it gets distilled down into a very basic pixelated visual representation. And this is the image that gets sent downstream to the transmitter. Now, the Argus 2 had a resolution of 60 black and white pixels. So basically, it needed to be able to convert whatever you were looking at into 60 pixels. This image information is then transmitted wirelessly to an implant on the retina. The receiver takes these signals and sends them to that surgically implanted retina electrode. The electrode sends small jolts of electricity to the retina and stimulates the retina in specific patterns. These electrical signals can then get sent through the optic nerve and into the visual cortex in the brain, which the patient interprets as perception of vision. This technology came out in 2013, and I thought it was absolutely revolutionary. This device gave patients with blinding retinal conditions a second chance at vision. Here's a previously blind archer using his Argus Bionic retina to hit some targets. And this video is from almost 10 years ago. It's pretty impressive. But it wasn't all sunshine and rainbows for Second Sight and their Argus implant. Unfortunately, Second Sight and their founder/CEO at the time, Robert Greenberg, had difficulty in figuring out how to make their retinal implants financially viable. Second Sight sold these Argus 2 devices for $150,000 a pop, but they were blowing through money for research and development, sales staff, and regulatory specialists to make sure they were doing everything above board for the FDA. And for patients, just receiving the implant was the first step. Each patient would need to work with vision rehabilitation specialists one-on-one for months to years to figure out how to navigate the world with their pixelated vision. One Argus patient mentioned that when they factor in the cost of the surgery, the Argus 2 implant, and all of the rehab services, the total cost of their bionic vision was $497,000. So the math didn't add up for these bionic retinas, and in 2020, Second Sight announced that their head of research and development and their CEO had left the company. They laid off the majority of their employees, and they auctioned off their manufacturing equipment, scientific instruments, laptops, just about everything. They were teetering on the edge of bankruptcy and outright collapse. And the worst part, as the company was imploding, no one informed the hundreds of patients with these Argus 2 implants in their retinas. These patients were totally left in the dark. Pardon the pun. Horror stories started coming out of patients who learned the hard way that their retinal implants were no longer being supported. Ross Dewar, who received the Argus 2 implant in 2019, started to feel dizziness and vertigo in 2020. His doctor wanted to get a brain MRI for him to rule out a brain tumor, but first they needed to contact Second Sight to figure out if it would be safe for him to receive the MRI with his Argus 2 implant. Remember that the M in MRI stands for magnetic. An MRI machine becomes a giant, very powerful magnet once it gets turned on. It has the power to very forcefully pull in wheelchairs, stretchers, IV poles from across the room if they're magnetized. So if you have a metallic chip implanted into someone's retina, you need to be 100% certain that that implant will not move at all during their MRI scan, or else that can lead to a potentially fatal accident. And so Ross and his doctor spent several weeks sending letters, calling, emailing Second Sight to see if he could get his brain MRI done. But with the company collapsing, there was no one to answer his calls. He wasn't able to get his brain MRI done to evaluate for a brain tumor. And remember that archer hitting targets using his Argus 2 device? His name is Jerome Perk, and in 2020, his video processing unit fell to the floor and broke. He attempted to contact Second Sight to send him a replacement, but he was unsuccessful. So he was kind of stuck with his retinal implant and no computer to connect it to. Fortunately, he was able to find another Argus patient who was no longer using their system and a doctor with a spare video processor. So they were able to hobble together a refurbished system for him to turn the lights back on. But these stories kind of show the double-edged sword of technology. With a constant advancement of new hardware, new software, companies eventually stopped supporting old devices. We're now on the iPhone 15, the 10th generation of the iPad, and the Samsung Galaxy S23. iPods are no longer a thing, let alone CD players or Walkmans. With new technology constantly coming out, it seems like the time cycle of technology becoming obsolete is happening quicker and quicker. When it comes to a cell phone, for example, it's relatively easy to trade out an old Nokia or BlackBerry to the latest iPhone. But if your old technology consists of a computer chip that is scarred into your retina, it's not quite so easy or safe to just trade it out. And so we really need to be cautious when introducing all this new and exciting technology to people and think hard about how these patients will be supported for decades after their surgeries. But that brings us to the next generation of brain-computer interfaces. Elon Musk and his team at Neuralink have taken the lessons learned from Dr. Donahue and BrainGate, as well as Second Sight and their Argus implant, and they're now developing their version of Bionic Vision. Elon recently hosted a show and tell event with Neuralink and shared all the latest advancements they have developed to push the field forward.
All right, welcome to the Neuralink Show and Tell.
There are 3 key improvements that he highlighted over previous generations of brain-computer interfaces that will help Neuralink actually make this more available to the masses. Let's first summarize how Neuralink's technology works and then go through those key features that make it a game changer. As opposed to the retinal implant like the Argus, the Neuralink implant is a brain implant. So the first step is that patients will need to undergo neurosurgery to receive the technology. What the neurosurgeon will need to do is drill a hole in your skull. This is what we call a craniectomy. Then they need to remove the tough outer layer of the tissue protecting the brain called the dura. Then they want to insert thin, flexible threads of electrodes into the brain. Remember that these electrodes are basically the wires which allow the Neuralink scientists to send electrical signals back and forth between their computer chip, which they call the N1 chip, and your brain. Then they fit that N1 chip, which is about the size of a quarter, into the hole in your skull that they made. Then they close up the skin on top, and congratulations. You are now the proud recipient of a brain implant. And remember that retinotopic map we talked about? How our brains are organized in a specific way so that when we see things, for example, a dot in the right side of our visual field, then the left side of our visual cortex will fire. So the thought with the Neuralink implant is, since those electrodes are implanted in precisely mapped out locations in your visual cortex, if they activate the electrodes in your brain in specific patterns, this will allow you to see pixelated images even if you don't have an eye. Okay, so we have the N1 chip successfully implanted into your brain. Now what? Well, what they do next is connect it to a computer vision system. They take a video feed from a digital camera, and that feed is streamed wirelessly to a smartphone. And as we've seen with Meta or Facebook smart glasses, we now have the technology to create stylish, regular-looking glasses that have digital cameras in them. So the digital cameras send the video feeds to a smartphone, which most of us already have in our pockets. That smartphone will take the video information and convert that into a neural signal, which can get wirelessly transmitted to the N1 implant in your brain. Then the N1 chip can send those electrical signals through the electrodes directly into your brain in specific patterns so that you'll be able to see what's around you. And here's a visual representation that the Neuralink team shared at a press conference of what they're hoping to deliver with their visual prosthesis device. Here's a photo of some European-looking street corner on the right. And on the left, we have their pixelated representation of that same image. If you squint your eyes a little bit, you can start to see the details on the pixelated image. For example, you can see the lamppost right in the center of the image, or you can see the edges of the buildings lining the street. Obviously, there are limitations to this computerized vision. There's no color, and it's composed of those pixels you would create by stimulating certain areas of the visual cortex. But this is still an impressive demonstration from Neuralink. Okay, so now that we have a good understanding of what Neuralink plans to deliver with their technology, let's go through the 3 key features that they have shared that elevate their technology head and shoulders above what's been done in the past. The first key advancement that Neuralink has going for it is that their technology replaces rigid arrays with thin, flexible electrodes and a wireless interface. The benefit of these flexible wires is that each wire can be placed strategically in the brain with improved precision. The usual standard implant for brain-computer interfaces are rigid metal chips called Utah arrays that have tiny electrodes that stick out like needles. These electrodes are connected to copper wires so that electrical signals can be sent back and forth. Research studies on explanted brain implants have shown us that with time, unfortunately, the materials on these chips can degrade, or the brain can develop scar tissue around the chips, which leads to loss or degradation of signal. The other limiting factor with these arrays is their bandwidth, or basically the amount of data that they can send back and forth. Remember that Argus retinal implant that we talked about? The resolution of that implant was limited to 60 pixels. To put that into perspective, a typical 1080p high-definition screen has about 2 million pixels of visual information, whereas a 4K ultra-high-definition display has 8.3 million pixels. So in order for these bionic vision systems to start resembling what we'll call realistic vision, their bandwidth will need to expand by several orders of magnitude. The Neuralink team has announced that their brain implant chip, which they call the N1 chip, can record from 1,024 channels. For context, this is 10 times the bandwidth of the Utah array. At Neuralink's show and tell event, they announced that the next generation of their chip will have 16,000 channels of bandwidth. If you put one of these chips on each side of your visual cortex, that gives them 32,000 electrodes to deliver visual information to your brain. And with that increased bandwidth, the images that they can create will be much sharper compared to the images from the 100-channel Utah arrays in use currently. The other big innovation with Neuralink's technology is that all of this can be done wirelessly. With previous brain-computer interfaces, you would need to plug in a wire into your skull to get connected to the system. This obviously limits its use cases. But since Neuralink's technology can all be used wirelessly and will probably be paired with regular-looking glasses and the smartphone in your pocket, you could be out and about in the world with a fully functioning brain implant and no one would even notice. It'll basically be invisible. Here's a demonstration that the Neuralink team shared of a monkey charging their N1 chip wirelessly. You can see that they've installed a charger into a tree branch here, and when the monkey sits below the coil, it starts delivering a current to the N1 chip, allowing the battery to charge. Okay, so we have thin flexible wires and a small N1 chip that could deliver lots of data wirelessly, allowing it to be invisible to those around you. The next innovation that distinguishes Neuralink is their surgical robot. The Neuralink team showed off a live demonstration of their R1 surgical robot in action at their show and tell event. Now, remember when we talked about that retinotopic map and how visual information is organized in our brains? In order for Neuralink engineers to recreate accurate images of the world around us, they need to make sure that their electrode tips are inserted exactly where they want in our visual cortex. This requires precision to fractions of a millimeter. So they invented the R1 robot, which has the ability to grasp and precisely insert these electrode tips into a human brain while also dodging important blood vessels, even if that human's brain is moving slightly from their breathing. And here's the R1 robot in action.
There you go. That's the first insertion.
Now, believe it or not, using surgical robots to perform precise surgery is already a reality, and it's something we do on a regular basis as eye surgeons. Just like in brain surgery, in eye surgery, we have very small margins for error. Making a wrong move by just half a millimeter during eye surgery can make the difference between a smooth surgery with no problems and a complicated surgery with poor vision for the patient. And so during certain surgeries, such as LASIK or laser-assisted cataract surgery, we call in the assistance of surgical robots, which also have patient imaging and eye motion tracking capability so that we can deliver laser treatments into the eye exactly where we want on the order of microns. That is, fractions of a millimeter. So it's exciting to see Neuralink bring that same level of precision to neurosurgery and their brain implants as well. The last important innovation that Neuralink highlighted at their recent press conference was the future upgradability of their technology. With those poor Argus patients, we saw the consequences of what can happen when a corporation stops supporting or updating their implant technology. And with any medical device, especially ones that you are surgically implanting into people's bodies, companies need to think critically about how they can make sure that early adopters will be able to access newer and better versions of the technology. I mean, Neuralink hasn't even finished testing their N1 chip, and they're already proclaiming the great new features that will be in future generations of their brain implants. But what will happen to all the people who have the first generation of the implant? What often makes implant exchange difficult is the encapsulation or scar formation that occurs around implants. For example, in eye surgery, we place drainage tubes into people's eyes to help decrease the eye pressure in patients with glaucoma. There's a little plate that we place on the outside surface of the eye. The body identifies the implant as a foreign object, and usually after a couple of months, your immune system creates a capsule or layer of fibrous tissue around the implant to wall it off from the rest of your body. In brain implants, a similar process occurs. After that N1 chip is implanted, after some time, a fibrous capsule will form around it. And depending on the amount of scar tissue, the Neuralink engineers have probably found this out the hard way. Going back in there to replace or upgrade that implant can be a traumatic, bloody procedure. And so the Neuralink engineers are aware of this challenge and are developing different solutions to make the implant replacement process easier for both the surgeon and the patient. Remember that during implant insertion, there's a thick protective layer of tissue called the dura, which surrounds and protects the brain. This dura must be cut open to access the brain underneath. What they found is that if they keep the dura intact, meaning not cutting through it, then there's less scar and capsule formation that forms around the implant, which would hopefully make it easier to exchange in the future. But since the dural tissue is not being cut open, they are now dealing with a couple of challenges. One is figuring out how to insert these hair-thin electrodes through the tough dura without letting the tip bend or break. The other challenge is, if they aren't opening the dura, they actually can't directly see the brain anymore. And so trying to insert these electrodes in precisely the correct locations while also trying to avoid the blood vessels coursing through the brain becomes very difficult to do if they can't directly visualize the brain. They are now experimenting with different imaging modalities, such as injecting glowing fluorescent dyes into the vasculature to visualize the blood vessels in the brain. Although these are difficult problems that they're trying to solve, I'm optimistic that with all the brain power, engineering chops, and money that they have at Neuralink, they'll eventually figure this process out. What's exciting about all of this progress is that Elon Musk and Neuralink have openly shared that their goal is to scale up their operations and offer their brain-computer interface technology to more people than ever before. This technology won't just be the subject of college neuroscience lectures or medical conferences. Neuralink is hoping to deliver their brain implant chips to the masses. What we're witnessing is the birth of an entirely new industry, neuroengineering, which could very well change humanity as we know it. Now, as this progress continues, we'll need to think about the ethics and the power that a corporation will have if they have a literal direct connection between their software and people's brains and innermost thoughts. Whether we are ready to accept it or not, this technology is coming, and it'll probably come sooner than you think. I'm Dr. Michael Chua with Point of Hills Eye Care. See you next time.